Sensors help us understand our planet by monitoring important environmental characteristics. Marine scientists on board the RV Revell use sensors to study biological, chemical, and physical processes in the ocean by measuring temperature, water chemistry, and current speed, among other qualities, both in surface waters and at depth. Remotely operated vehicles like Jason deploy and service sensors on the ocean floor. These sensors are part of an underwater observation network of over 100 instruments, streaming data that can be used by researchers, students, educators, and the public at large. Continued monitoring alerts us to the magnitude of environmental changes affecting marine biodiversity and ecosystems. Once launched overboard, Jason descends thousands of meters through the water column to reach the sensors on the ocean floor. This map shows the extensive sensor network off the coast of Oregon called the Ocean Observatory's Initiative Cabled Array, which is maintained and operated by the University of Washington. At the bottom, the cabled array gives us insight into active underwater volcanoes like axial seamount and shows us the diversity of life in these extreme environments, in addition to monitoring earthquake activity and other geologic processes. Temperature probes have helped us learn that hydrothermal vent fluid reaches upwards of 300 degrees Celsius, shedding light on the adaptations necessary for life to thrive in these extreme conditions. The benthic experiment package collects data on several environmental properties such as temperature, pH, and carbon dioxide concentrations to create a more well-rounded picture of processes occurring in the deep ocean. In addition to cabled array sensors, scientists can use other shipboard tools to understand conditions throughout the water column. An onboard sensor package known as a CTD, which stands for Conductivity, Temperature, and Depth, collects data as it's lowered through the water. As the CTD descends, it creates a profile of the water column, illustrating how physical, chemical, and biological properties change with depth. Scientists collect water samples as the CTD comes back up by remotely triggering large gray bottles to close at various depths to collect samples. Back on board, students take bottle samples which will be tested in the laboratory to confirm chemical and chlorophyll readings from electronic sensors on the CTD. In the classroom, students can build basic sensors that work in much the same ways as these high-tech ocean sensors by creating simple circuits with mini-computers called microcontrollers. Temperature sensors assembled with 3D printed parts work similarly to those on the cabled array and can report temperatures at frequencies from seconds to hours. Here, a temperature probe is lowered off the side of the ship and has begun collecting real-time data shown on the computer screen. These student-built sensors can also be put in the environment for a number of weeks and collect data on an SD card, which can then be retrieved after deployment. Using the same microcontroller boards, students can easily assemble a pH sensor that emulates the pH measurement methods used in the benthic experiment package shown earlier. pH is determined spectrophotometrically, meaning an indicator solution is added to a water sample, causing it to change color. Based on the relative transmission of light of different wavelengths through the sample, the exact color, and consequently pH, is ascertained. Students calibrate their sensors using a range of known pH solutions to create a calibration curve of absorbance versus pH, which is then used to identify an unknown sample. Students can then test environmental samples like these CTD water samples taken from different depths and plot them on their curve to calculate an exact pH value. Using these sensors, students can understand ecological processes and changes that are shaping their local environments by monitoring terrestrial or aquatic areas near their home or school, like gardens, lakes, streams, or beaches. Sensor-based observations of our immediate environments can help us understand the local impact of large-scale global processes.